Hello everyone. Today lecture I will continue coupled mode theory. Specifically I would like to establish a generic form of coupled mode equations when there is some kind of small perturbations are there in the waveguide. So, we discussed also already that if there is no perturbation, that means simple waveguide, cross section is defined by dielectric constant epsilon A x y, and it can be represented in terms of refractive index profile x y cross section. It is just representative waveguide shown here, silicon on insulator waveguide. And then for this scalar wave equation, where we have used this E is the dominant electric field component, and omega square mu epsilon A, this comes here, and beta square, for example, it is a eigenvalue or the propagation constant that has to be solved from the eigenmode solver. So, if you just see this differential equation, you have this form of solutions you can assume. That means electric field is a scalar. I am not considering vector because it is only oscillating in a certain direction. So, dominant electric field I am considering x y z t. So, you will have some amplitude A m and profile E m for the mth mode, the field distribution, electric field distribution x y, and the phase part omega t minus beta m z. Okay. If you just insert this equation here E, then you get the differential equation for eigenmode, mth eigenmode. So, you can solve this equation, that is how you can get from here E m x y, series of distributions you will be finding, and series of solutions you will be getting beta m, that is what you are supposed to have. And each of this mode, if you are just getting, you can normalize that one with a normalization constant A m square to 1 watt, and then according to the orthogonality condition, we have E m star E m star, then it will be 2 omega mu by beta m. In principle, it should be something like that. We know that E m x y and E m star E n star x y dx dy, it should be equal to 2 omega mu by beta m delta m n. So, that is sometimes this beta, instead of beta m, we can just write square root of beta m beta n, because when m equal to n, so ultimately it will become beta m. Otherwise, m not equal to n, that should be equal to 0. That is the Kronecker delta function. And let us consider that okay, this is the waveguide 3-dimensional view, and standard input output side, this is a uniform waveguide defined by epsilon A x y, x y distribution is there, and along the z direction it has no change in refractive index even in the cladding or is in the core. And we assume that there is a perturbation started at z equal to z naught to z equal to z naught plus L, L length from this to this, it is L length. So, in this L length you have, along with that you have some dielectric perturbation which can be function of x, y and z. Okay. Now, we know that if it is the waveguide can support a number of modes, solutions are there. So, total field can be just, we can establish, we can just find total field in the waveguide by summing all the field along with their phase. So, that is if there are 10 modes, so 10 mode superposition, that will be the total field in the waveguide we can just consider. Okay. Now, if it is in the perturbed, if there is a perturbation is there, so in that case how your waveguide modes will be modified. This perturbation, obviously this delta epsilon whenever I am writing, that should be very less than original refractive index profile of the waveguide. That is a very small perturbation. So, for this small perturbation, what you could do, you can say that you are just breaking the orthogonality condition. That means, the modes propagating inside the waveguide, they are no more orthogonal, they can start interacting each other and they can exchange energy also depending on their some kind of certain conditions. So, if that is happening, so what we could say that in this perturbed region, the modified total electric field the total electric field can be written as somehow it is amplitude. Here this amplitude when there was no perturbation, that is z dependent amplitude is there. Now we say every mode, mth mode will have z evolution. As a function of z, it will have some kind of evolution. That means the field amplitude that can vary. So, if you all the modes, if it is starting with 1 watt and in the perturbed region, they will exchange power and they can be different after travelling. When the z equal to z naught plus L reaching, that time you can see some different value. It will not be no more, it will not be any more 1 watt. Okay. So, to deal with this type of equation, this is the assumption. We have considered that the amplitude will be varying, they will be interacting, energy will be exchanging each other. So, this is the thing happening. We can assume that this is the solution of the same differential equation whatever we have considered for eigenmode solution. Only thing is that the epsilon A will be replaced by epsilon A plus delta epsilon x. So, that is what we have replaced here. In this equation, I could write this thing, and I do not have any z dependent well defined function like beta m z. Instead of that, I have beta m z is there as well as additional function a m z is there. That is the reason I cannot write del z equal to minus beta square. We cannot write. Instead, what we can write, this is the epsilon modified epsilon a, and instead of beta square, I just retain del to del z 2 along with the del 2 x 2 del 2 del y 2. So, that means I can assume that this when the dielectric constant is modified, then I cannot write just simply beta square. Instead of that del 2 del z 2 operator I include, and I can assume that the solutions will be modified electric field solutions, which will be superposition of all the modes where the amplitudes will be evolving as a function of z. That is the assumption. Okay. This is the background. So, we have, if we have a perturbation, then the mathematical framework, all the governing equation are now set. Okay. Now, we need to solve this equation. How to solve that? So, I just retain whatever I have discussed so far in this black marked and white fonts. All this thing we have whatever discussed in the previous slide, that I have retained here. So, here this m and this m, if it is different, it would be written a delta m n something like that. Otherwise, they are same mode, that means that is how we normalize. And we retain that perturbed equation, wave equation, and perturbed solution, z dependent function additional component in the solutions we have assumed. Without that, we have simple solution earlier what is there. So, this is the perturbation, these things I retain, this figure also I retain, z equal to z naught to z equal to z naught plus L length something is there. So, to solve this equation, I have this solution. So, what I have to do, I have to find the del 2 del x 2 of E, what is the value, this one of E, what is the value, this one of this means this is the solution I have considered, and this one whatever the value, then that value I main thing is that to solve this differential equation, this solution you assumed, that solution you just insert there and try to see what is the outcome. If you can get some simplification or some constant like a m z, if you can solve or not. Our intention is that if we can solve a m z, then we know how mth mode is evolved in the perturbed region. So, ultimate goal is to find out the value of a m z as a function of z, how the amplitude is evolving, whether it is reducing or it is increasing. It can, if mth mode is actually gaining some power energy from other modes, then it will be increasing, and if it is losing, then it will be reducing as a function of time, a function of z, and it will be losing to other modes. So, that is the whole story. So, if I just consider E this one and then try to find out del 2 E del x 2. So, del E 2 del x 2, if you do x y dependent function only this one, otherwise a m z that will be retained. So, I write a m z del 2 E m, meaning this is actually x y, okay, del x 2, and phase part z dependent function, time dependent function, I am taking partial derivative with respect to x. So, similarly, this is the only y dependent function is there. So, del 2 E del y 2 I can write same way. So, only thing is that instead of del 2 d E m x y by del y 2, here instead of that it was del x 2. Okay. Now, we have to find this factor, this term del 2 del z 2. So, if I try to do del 2 del z 2 on this, if I just operate on this thing, then we have two z dependent function, amz is there, that is what we have to solve, and here also exponential term z is there. So, two variable is there, z dependent function is there. So, we have to do partial derivative for this two z dependent function. So, first of all, I cannot just directly derive like del 2 del e del x 2, similar way we cannot do, we just first try to make del e del z first. So, del e del z first means I just make a derivative first term, retain this second function, and then second term I will be making derivative with respect to that, and other thing will be retained amz, this one retained, and with respect to this one partial derivative z minus j beta z it will be coming. Then now we have two terms, this is also z dependent term, in each term there is two variables z dependent function here, this is also z dependent function, this is the function. So, here also this once more if I do del 2 d del z 2 here, then I will be getting two terms here, two terms here. Okay. You can do by yourself, I am just writing directly the exact formulation here. So, here if you see this is the value, if you are just making a derivative, once more derivative d 2 a m by d z 2 e m x y, this factor, and then this factor j 2 beta d m. So, this should be corrected, this should be z, not d j. Okay. And then one more function will be like this, beta m square like this. So, I have now this del 2 del x 2 term, whatever the value I have now is there, and I have also del 2 del y 2 term is there also, and del 2 del z 2 term also I have all this term. So, what I will do next, I will be just inserting this into this function here. So, whatever the things, okay, I just written down all these three terms in clean way, this term whatever the thing here, and this term whatever the thing here, and del del z 2 term I operated on this, then I have three terms, first term, second term, and other two terms will be similar, that is why it is added by 2 beta m minus j beta 2 beta m, and this is z also, this is should be corrected del del z. Okay. So, now what is the next thing? Next thing is that yeah, this is one thing I have approximated. We have considered this AMZ, since it is a weak perturbation, this is a weak perturbation, AMZ is a slowly varying function as a function of z. It is not that suddenly energy will be changing. So, perturbation is very small. So, if any energy exchange is happening, that is in a slow process, as a function of z it is a slowly varying things. So, in this term you have dAm dz as well as this one is there, right. So, in that case second order derivative with respect to this one I can just ignore. So, this is the approximation we did, that we can assume that the second order variation can be ignored. If any abrupt change is there, that has to be kept outside the scope of this process, this derivations. So, I just consider slowly varying function. If it is slowly varying function, then this can be cancelled. So, ultimately you will have this one and this one del 2 del z like this. So, we can just now clean up that, okay, this is del 2 e del x 2, del 2 e del y 2, del 2 e del z 2, this has a two terms. So, what is next? Next is you just insert all these three terms here, 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 multiplied by e here, you just inserting in this equation. So, once you insert, then what you return back? You get first term whatever you are getting, that should be added with this, should be added with this. So, this one means you are basically this term adding, and this term adding, and this term you adding, and then rest of the part this thing we are just omega square mu epsilon a times this one means this full function I have just added, and plus delta e omega square mu delta e epsilon x y z full term I am just writing down. Okay. So, that is good. So far I have to use this term, and this term as well as this term, because this is the second order derivative with respect to z, two terms are there after ignoring d2 e by dz2, d2a dz2, this term we ignore, then we get this thing. Okay. So, after simplification, after inserting and you are doing little bit of simplification. So, what you get in the first term, you are getting this one, and from the third term, first term, second term, third term is this one, and this is fourth term, and this is your fifth term. Okay. So, all these you are writing, that you are adding, and that should be equal to 0 here we are writing. So, now we are almost done. Now, you see we can simplify here. The first term I can write, this is one term is there. So, if you just simplify like this, then am z em x y, this one, and sum over this one term, and another term will be coming this one, and this one is the third term. I can rearrange to write down this way, one term and the second term and third term we can write. So, second term and third term, if you see, second term you have this evolution of z am, mth mode, how it will be evolved, and third term you have this perturbation, and first term if you look carefully, it is appearing like this equation. So, when the waveguide is unperturbed, that because we consider unperturbed waveguide, when it is unperturbed waveguide, the Morse field distribution solution is this one. In perturbed waveguide also we consider same mode field distribution. Apart from that, you have some kind of slowly evolution AMZ is there. So, if I just use this one here, here you see this one EMXY, if you just multiply here, that means you are getting this expression, that means this one equal to 0. This term I can directly put equal to 0. Exactly, I just try to use this expression. Instead of EM, this one is the function EMXY, e to the power j omega v t, it will be there. So, I can just multiply this one and this one, that will be equal to 0 according to this expression. So, now I have left over that this term is 0, then now two terms are there in the left hand side. So, in this equation finally, we left over with these two terms. Okay. So, now you see this is the equation we get, because in this equation if you see minus sign is there and there plus sign, and this one I take to the right hand side. So, if I take to the right hand side, what we get? Okay. Now, you see we get this equation, okay, this equal to this, and what we did here, because both side you have j omega t, it is also j omega t, both side, that e to the power j omega t term I factor. So, what I get? Left hand side I get this one, e to the power minus j beta m z, and right hand side also m, and I am writing a different index here for the right hand side. It does not matter, m also can, here it is varying from, say if it is 10 modes are there, your m you are varying 0 to 10, right. Here also you can put independently, you can put in 0 equal 0 to 10, then it is also it will give same value, because left side and right hand side function is different. Only thing is that this index runs for all the modes. Here also this index runs for all the modes, because these two terms are identical. We could write am both side, that is fine, but if we treat them independently, then we can see any other certain mode, for example, say E equal to k x y, if I operate, if I try to see with respect to k x y what is happening in both terms. To compare that, I just use the separate index here, this is m and this is n. I think without any loss of generality, this is actually correct mathematically, both side. Instead of writing m here, I just converted n. Similarly, am is converted into n, em is converted into en, and beta m is converted into beta n. So, that is different mode, different type of solutions I can just think of. Good. So far so good. Now, what we do here, you see this is the expression we have. What we are trying to do? We just multiply E k star, it basically what you are multiplying E k x y e to the power minus j beta k z. Obviously, you can also multiply e to the power j omega t also, that is fine, because I have not used e to the power j omega t terms both side. So, that is also I do not need to consider time dependent part, only space dependent part is there. So, I want to use this one complex conjugate, I want to multiply both side. I multiply this one this side, I multiply this one and this side, okay, and then integrating over xy plane. So, the region will be clearer why I am doing so. If I just multiply E k x y to the power star, that means E k star x y, obviously you should keep in mind that this field can be a complex value E m x y, any field distribution that can be a complex, that can be written as something like that a x y plus I b x y, something like that you can express also. So, that you can say that at any position to position phase can be also different, that type of complex thing you can think of. That particular coordinate system you can see whatever the angle 10 b by a, another position their phase will be can be different, they can be different oscillating in the different phase, that always happens also, we know that. Sometimes first order mode, higher order mode we can see that one point one phase, another point maybe it is oscillating in with the another phase. Okay. So, that mathematically it is correct. So, now if I do so, what we get? So, left hand side and right hand side I have written in two box, you see here. So, first I E k star x y, E m x y d x y, and I have multiplied e to the power z beta k z, and originally it was e to the power minus j beta m z was there. So, if you multiply then you are getting e to the power j beta k minus beta z, and E k star I multiplied here E m this one and dx dy, you are integrating over this one, and obviously this is amplitude, slowly varying amplitude of every mode, that is what we are writing here, that derivative of that one we are having, and both side you have summation, this is summation here, and here also what we do, we have here you have this term, you are multiplying E k star, this side you are multiplying here E k star x y, and you have right hand side delta epsilon x y, the perturbation term is there in the right hand side. So, this equation if you try to interpret specifically, that left hand side you see the evolution of mth field, and right hand side that is actually because of this perturbation all other modes are disturbed, and all other modes how much it is contributing to the mth mode, that is the left hand side. So, this side is the source and left hand side is the actually it's gaining at mth mode, how much it is evolving gaining, that is actually the interpretation here. So, by the way what I was talking that we are multiplying both side E k star and integrating, and here I have used n, index n it was used. So, beta k multiplied e to the power z j beta k z multiplied and minus beta n we have written here. Okay. Now, look carefully. So, left hand side if you see, you have kth mode, that is fixed, one particular mode, and you are trying to see all the mode, this m is running from say 0 to some n, whatever number of modes. So, that means I am just running this field and taking multiplying that and integrating every mode, what is the value we are getting, that is I am summing, along with that corresponding things will be there. But if you just concentrate only on this integration, you know what is this value, when k equal to m, when k exactly equal to m, then only this factor will survive. Otherwise, because of the orthogonality condition, we know that earlier we have discussed that E m x y E n star x y dx dy, that should be equal to 2 omega mu by beta m delta m n. So, only when m equal to n, then only this value will be 2 omega mu by beta. If m not equal to n, that will become 0. So, that means when I am running m from 0 to all modes, and this E k is the kth mode, when m is reaching to kth mode, then only that particular term will be surviving. All other term, because of the orthogonality condition, this Kronecker delta function, that will be 0. So, left hand side only I will be left over by only one term, not all the m terms you need to consider. That is the reason we multiply this one and integrate. So, that left hand side will become easier, it is simpler. Okay. So, now what is that next? So, left hand side if you just do, this one will be 2 omega mu by beta k for example, and this exponential term, you know, beta k equal to m means this will be 0, that will be 1, this factor will be 1. So, this value will be 2 omega mu by beta k. So, this thing multiplied by 2 omega beta k, and m will no more be summation, because it is only one term, it will be surviving. Okay. So, we have left hand side, if you see in the previous, this is the left hand side, j to beta k 2 omega mu by beta k, that is coming out of the orthogonality condition, power 1 watt multiplied by 1 watt power of course, and dm by dz, because k equal to m only, that is surviving. So, I have just written m equal to k, mth place I have just putting k value. And right hand side, if you see, what was the right hand side? So, right hand side if you see, here also you have E k star, E n star, but this one is there, in between you have a x y z function is there, and n you are running over. So, in this case if you see, because delta epsilon x y z is involved, so it is not so easy like here we could write 2 omega mu by beta k, this integration, that is the orthogonality condition, but here orthogonality condition is breaking because of the presence of delta epsilon here. So, you cannot just simply write like this, whatever value comes you have to use that one, but you have to run from n to, because it looks like that normally if delta epsilon is 1, then it would be 2 omega mu by beta k, beta m or whatever delta k n, something like this. But once it is there, as if you are considering because of this perturbation, you are operating this perturbation to the all modes, and bit by bit how much overlapping it is coming here. That means, you are just operating on this nth electric field, and then you are taking projection, how much it is after operating, how much projection it is there on the kth mode. It is something like that. In vector mode you can write something like that, if it is a vector E k star dot delta epsilon E n star x y. You can think of this is actually operating on this, whatever value it is coming, you are taking dot product with that, projection with that, that is what overlap this meaning actually. So, if it was just 1, it would be something like that, it make no sense, no perturbation, that means it is left hand side, right hand side, easily you could relate. So, since we cannot do that, right hand side we just keep as it is, n summation we keep, left hand side it is like this. Then what you see, this expression left hand side I just only keep this side, this one, and beta k I can take right hand side. So, you see this is j to beta k. So, numerator beta k is there, because I cannot cancel this one here, because beta k can be considered as a which direction it is propagating, depending on the direction actually plus beta k and minus beta k we can consider. Minus beta k is the forward propagating wave, representing when it is e to the power j omega t minus beta k z, it is forward propagating wave, and if it is e to the power j omega t plus beta k z, that means it is backward propagating wave. So, that is why depending on that this sign we can use, forward propagating wave or backward propagating wave, but here since it is coming out of power. So, in case of power there is no meaning for power, plus sign or minus sign, right. So, in this case 2 omega mu and beta k I think mode I have taken. Okay. This I want to take to the right hand side, so that I can get dak by dz. So, dak by dz, this one in the left hand side, and right hand side if I put, we will be getting like this, minus j beta k by beta k. This has no sign, this is absolute value we will be taking, but top one I will be considering whether I am considering positive propagating mode or negative propagating mode, and this one will be there, omega by 4 will be there. I have taken omega by 4 within the sum, but it could be omega by 4 can be outside, because n you are just running over this thing. That means kth mode you are seeing what contribution coming to the kth mode, because of the delta epsilon to all other modes, n is running, right. Delta epsilon you are just n as it is running from 0 to 10 or something like that, how many modes are there, that you are just operating and then looking into the kth mode, what is the projection, and that will be actually you can read like that, that is the contribution accumulating for kth evolution. dak dz means how it is actually evolving as a function of dz. What is the slope of akz, this one, this akth z dependent AMZ we consider mth mode, we are considering just kth mode, any kth mode, arbitrary kth mode, whatever how it will be evolving we can write like this. So, what we have done, we have just a little bit contracted this one, just represented Ckn, that is the overlap part that you are expecting omega by 4, this particular term up to here we write Ckn. Just if I run, if I change n different mode, if I see n equal to 1, 0, 1, 2, 3, 4, so on, then I will be writing Ck, suppose kth mode is 1, then I will be writing Ck C1 0, then I will be writing here E0, this would be E1. So, first order mode and fundamental mode along with the delta epsilon, whatever the perturbation is there, then you are integrating over entire cross section multiplying omega by 4, that actually we can calculate numerically, all these we can calculate by mode solver. Once we know the mode solver and once we know field distribution through mode solver and once we know the perturbation, then we will be able to calculate what are the values of Ckn. So, since it has to be estimated numerically and we can insert in this equation, so we cannot consider this solution entirely analytical, semi analytical, some part is numerically you need to compute. So, whatever you are computing, that value you can consider, then you can just try to see, once you know that value, then you can see how to simplify this equation. Our ultimate goal is that I have to solve AKZ, kth mode, how it will be evaluating. K can be any mode, first mode or second mode or third mode and so on. Okay, that how it will be evolving, this is the final equation. So, keep in mind that this is the expression you have to always keep carry forward. Whenever any particular perturbation things are known, then you will be able to calculate Ckn very easily and you can put down here, then you can actually estimate what is the evolution for the kth mode. So, this is called actually generic form of coupled equation. So, this is the equation, it is very important, is the base of coupled mode theory. Of course, it is a weakly guided coupled mode equation. Why it is coupled mode? You see, it is coupling kth mode to all other mode via these terms. So, it is a sum. So, you are for kth mode evolution, you see the contribution coming from all the modes, and how that contribution coming? Because of the perturbation. If there was no perturbation, no modes will interact each other, they will not exchange any energy, and because of the presence of delta epsilon, this one is there, and depending on that value you can find out how much contribution coming from each of these mode, and that you sum together, then you will find this value. At the same time, if you see here one additional term is there, okay, that is very important, we will discuss that, that is beta k minus beta z. You are just changing, you have a particular mode, that is fine, and you have a particular propagation constant, fine. Now, I want to calculate Ck in this one for E0, E1, E2, all the fields I want to see here, and corresponding beta value also will be coming in the exponential. So, whatever the value it is there, that also is responsible for the evolution of kth mode. So, this is how you need to know. So, this is a very important equation for integrated optics or photonic integrated circuit. So, anything coupling, any device, any deformation, any modification, any engineering you want to do, you can just that engineering you can consider as a delta epsilon, okay, and that delta epsilon actually quantify Ckn, how much it is contributing energy transfer from one to another. Obviously, whenever you see this one, the dimension will be coming as a per meter. So, per meter travelling length, how much it will be contributing. If you just put radian per second, electric field volt per meter, sorry, the dielectric constant, here also you have epsilon 0, delta epsilon r or epsilon 0 delta n square. That means, it is farad per meter is there, and volt per meter, farad per meter and meter square. So, all this together radian per second, if you just combine all this together, then it will be per meter. So, that means, that is the strength per meter contributing for nth mode. So, when I say Ckn, that means contribution to kth mode because of the nth mode. So, nth mode is contributing to kth mode, that is how you have to read Ckn. Okay. That Ckn will come here, n can be 0, whatever the value you can calculate here, n can be 1, whatever the value you can have, and k you are just targeting only one particular, you are focusing on only one particular mode, kth mode. Kth mode, how much it is evolving because of the all other nth modes. So, that is what we can calculate and put here all the terms we have to include, then we can see that how much kth mode is being evolved. That is the basic thing of the coupled mode equation, and this is called actually generic form of coupled equation. So, lot of devices we will be explaining starting from this one. Fine. Now, next we clean up. So, now we see that kth mode, this is your field distribution Akz and Ekxy e to the j omega t, and this is the perturbation, and in terms of refractive index we can write. Suppose some perturbation, for example, in this case, in this region somewhere you have a perturbation that some silicon is removed completely, silicon core, some silicon is removed and then silicon dioxide is involved. So, incorporated there, some little bit particular point, some perturbation you have created, maybe some etching is there and then oxide is there. That means that region, what is the perturbation? That means epsilon 0 delta n square, because silicon was, refractive index was Nb, sorry Nd silicon, and silicon substrate is Ns. Now, delta n square you can write, delta n square, that particular region delta n square will be equal to delta Nd square, that means device layer refractive index minus that means it is Nd square minus Ns square, that is actually delta n square. That means instead of device layer you have silicon, that means how much dielectric constant you have changed or delta n square change, Nd square minus Ns square. So, that much if it is changed, and then you have to see how much area that is, that type of defect is there, that particular area delta epsilon is there. So, you have to integrate only that area to find out Ckn. Okay. So, perturbation is there, that entire cross section you do not have any perturbation probably, maybe only a particular region, some this region to this region perturbation is there, that particular region you have modification of perturbation, change of refractive index, that refractive index, and then that particular region this delta n is non-zero, and obviously field strength is there, kth mode field is there, nth mode field you have solved already numerically, that you can use and integrate only that perturbation region, then you will be getting Ckn. Okay, that is easy to calculate. Once you know mode profile and you know where is the perturbation, then you can calculate Ckn. Okay. So, now this is your Enxan, this is kth mode and nth mode, that they are actually field distribution we have written, both field will be there. So, I can say that I am just getting what is the evolution of the kth mode. Similarly, I can concentrate, instead of k I can write some other mode, k can be 1. Initially I was considering k equal to 1, you can consider k equal to 2, what is the evolution, then you can also get similar type of equation also. Okay. We will discuss that in course of time. Suppose normally in waveguide you can have only few modes will be there, you will be designing single mode waveguide, only one particular mode will be there, or maybe 2 modes maximum you can handle, or 3 modes, and maybe also single mode waveguide you are handling one mode this side positive direction, another mode reverse direction. So, that means most of the time you will be dealing with only coupling between 2 modes. Okay. So, coupling between 2 modes whenever you are considering, then you need to have only one term, because you are considering, suppose you are considering only kth mode and only nth mode, n is not running from 0 to all the modes, just only one specific mode n and one specific mode k, then in that case right hand side you will have only one term. Okay. That means I can say the kth mode evolution, how much kth mode is increasing as a function of z or decreasing as a function of z because of the nth mode. So, I can restrict our discussion between 2 modes, kth mode and nth mode, and kth mode can be fundamental mode in the forward direction and nth mode can be fundamental mode in the reverse direction, that can be also 2 different modes. So, they are coupling, when they will be coupling they will be propagating in the opposite direction, what would be the evolution, when they are propagating in the same direction, what would be the evolution, that will be our subject for the next lecture. Okay. Thank you very much.